Jnanam paramam dheyam. Knowledge is supreme.
Welcome back. Let us now consider another method of computing this maximum value of controller gain, which can be used or for that particular example, or in general another way to assess the stability of a feedback system in Laplace domain, and that method is known as direct substitution. So, direct substitution method directly gives you value of controller parameters when system reaches stability limit. Because if you see the effect of Kc or the controller gain on the stability of the feedback system with 3 CSTRs, what we see that for a small value of Kc, the system was almost very much stable without any sustained oscillation. As you keep on increasing the value of controller gain, the system oscillations will increase till a value of Kc equal to 64. The system just has sustained oscillation, which is also known as marginal stability, and then any value of Kc greater than that will result in growing oscillations or instability. So, there is another way of calculating this limit when the system has sustained oscillation, and that is known as a direct substitution method. So, what you do is you substitute S equal to I omega in the characteristic equation. So, what it means is it tries to find out the value of the controller parameters at which the poles will lie on the imaginary axis, that is condition when poles of the closed loop system lie on the imaginary axis. Okay. So, let us apply this method to our example of 3 CSTRs. For which the characteristic equation was s cube plus 3s square plus 3s plus 1 plus Kc over 8 equal to 0. So, now we substitute S equal to I omega. So, what we are going to get is I omega cube plus 3 I omega square plus 3 I omega plus 1 plus Kc over 8 equal to 0, which on simplification what we get is minus omega cube I minus 3 omega square plus 3 omega I plus 1 plus Kc over 8 equal to 0, and then we bring the real and imaginary terms together. So, what we will have is 1 plus Kc over 8 minus 3 omega square, that is the real term, plus 3 omega minus omega cube I equal to 0. So, when we say this equation is equal to 0, which is same as 0 plus 0 I, so we can equate the real term to 0 as well as the imaginary term to 0. So, that will give us two equations. So, what we get is from the imaginary term equal to 0 gives us 3 omega minus omega cube equal to 0, or omega into 3 minus omega square equal to 0, that is omega equal to 0 or omega square equal to 3. When we say real term is equal to 0, that gives us 1 plus Kc over 8 minus 3 omega square equal to 0. When omega is equal to 0, we will get 1 plus kc over 8 should be equal to 0, and when omega square or kc should be greater than minus 8, and when omega square is equal to 3, what we get is 1 plus kc over 8 minus 3 into 3 equal to 0. So, kc equal to 64. And so, what we see that this again is automatically satisfied, as we have kc greater than 0. So, we again get the maximum limit on the controller gain, which is same as the one which we obtained by using Routh-Hurwitz criteria, that if you have a controller gain of 64, the closed loop system will have sustained oscillation. If we increase the gain, it will lead to instability, and if we reduce the controller gain, we will have decaying oscillations. So, kc should be less than equal to less than 64 for stability. So, by using this method also we can compute with the stability limit, or what is the maximum value of controller parameter which we need to use in order to satisfy the stability criteria, or in order to ensure that the feedback system will remain stable. Now, all this information is typically represented in the form of a root locus diagram, which will be used to design a feedback controller. So, root locus diagram is the locus of poles of the closed loop system as the controller gain goes from 0 to infinity. So, it is the locus of all the poles of the closed loop system as you move from an uncontrolled or open loop process to a closed loop process with infinite gain. Now, this is always plotted as a trajectory of controller gain. So, if we are doing this diagram for a PI control, so we will have one root locus diagram for each value of tau I. In same way, if it is a PID control, we will have one root locus diagram for each value of tau I and tau D. So, you can see that if we have a PI controller or PID controller, we will have large number of such root locus diagrams which we will have to draw depending on the values of tau I or tau I and tau D. So, how does this root locus diagram look like? So, if we see the 3 CSTR example, this is how the root locus diagram will look like. So, you will see that the root locus starts with a point which has a triple root of pole equal to -1. So, for 3 CSTR system, when Kc is equal to 0, at that time the closed loop transfer function is Gp equal to, so in that case what we have is s cube plus 3s square plus 3s plus 1 equal to 0. So, which gives me s equal to -1. So, it is a triple root. So, all the root locus diagram will start with a point of -1, and you can see that as the Kc value of the controller gain increases, one of the root moves along. So, if I draw it here, one of the root moves along the real axis towards negative infinity. So, it is never going to cross the imaginary axis and will never go into the right half plane. The other two roots actually bifurcate into complex conjugate roots, and they have the real part which is decreasing as you increase the controller gain, and when the controller gain reaches 64, you have a pair of complex conjugate roots. If you increase the controller gain, it will go into the right half plane. So by using representing this by representing this closed loop behavior by using root locus diagram, you can again represent what is the maximum value of controller gain which you can have. Additionally, the additional information which root locus diagram also provides is the nature of instability. So here it shows that a pair of complex conjugate roots are moving into the right half plane. So that means the closed loop systems will have growing oscillations. So root locus diagram additionally gives you an information about how does the response of the system look like even before the controller gain value is less than 64, let us say some value around 50. It will say that the system will have decaying oscillations. It will also tell you what is the corresponding damping coefficient. So, you can also calculate the period of oscillation and all those things. So, root locus diagram kind of condenses all this closed loop information along with the limit of the stability. So, this is a very commonly used method to represent the stability analysis data for a closed loop system or a closed loop feedback system, that you draw this root locus diagram and then that will tell us what is the maximum value of controller gain which can be used for that particular system. Maybe it is a P controller, PI or a PID controller. So far we have seen these two methods in the Laplace domain. One was the Routh-Hurwitz criteria and the other one is the direct substitution. Both these methods give you a limit up to which the controller gain can be increased or controller parameter can be changed, so that you maintain the stability of the closed loop system. Now let us say we have a blender. Blender is also a very commonly used chemical engineering piece of equipment. So where you have a stream of flow rate W1 or the mass flow rate W1 at a mass fraction of x1 is coming into the system, and what you desire is some particular fixed purity x. So in order to achieve that, you generally add a blending agent which is a pure component, so that you can achieve the desired value of the product purity. So typically if I am using a feedback control on this system, the system will look like is, you will first analyze what is the corresponding purity. It will be given to the controller where there will be some set value or x set. It will be given to a controller, and then that controller will change the flow rate of this blending agent. So for one such example, the process transfer function, which is the transfer function between this product purity and the flow rate of this blending agent, that can be given as 8.33 10 raised to minus 4 over 3s plus 1, and we can again see what is the effect of controller gain if we are using a proportional controller, and we can make an assumption that measurement is instantaneous, wall dynamics are fast. So in that case, if we are trying to do the analysis in the Laplace domain, what we will find out that the closed loop transfer function is 1 plus Gp, Gc, Gv, Gm equal to 0. So we get 1 plus 8.33 10 raised to minus 4 Kc over 3s plus 1 equal to 0, which on simplification will give us 3s plus 1 plus 8.33 10 raised to minus 4 Kc equal to 0, or s equal to minus 1 minus 8.33 10 raised to minus 4 Kc over 3. Again, this is a reverse acting controller, so Kc is always greater than 0. So you can see that S is always negative for any Kc greater than 0. So what we will realize that the feedback system or always stable. Now let us slightly tweak this system and try to look at a more realistic picture. What we are doing here is that we are measuring the composition, and accordingly the feedback system is taking an action. Now composition measurement is very slow. So typically temperature, pressure, level, all or even flow, all these things can be measured almost instantaneously, and there is almost no lag in terms of the change in the variable and what you get as the measured value. However, same cannot be said about a composition. Composition measurements are very tricky, and even though we have sophisticated instruments like GC, it will still have some amount of lag by the time you have the measurement in a digital form. So even though I am saying that the measurement is almost reliable, what typically ends up happening is this transfer function is like this, where you have some delay of amount. So measurement is delayed by an amount of time equal to Tm. So that is known as a measurement delay. So it is a very common feature whenever we are working with composition measurements. So let us say what happens to this stability analysis if we have some measurement delay. So with measurement delay, what we have is the closed loop transfer function is now which on simplification will give us 3s plus 1 plus 8.33 10 raised to minus 4 Kc into e raised to minus Tms. So now you can realize that this is no longer a polynomial. Because of this exponential term, because of that we cannot directly use the method of Routh-Hurwitz to assess the stability, or even the direct substitution method will not be directly applicable. So in that case, so that is a major limitation of Laplace domain analysis. So whenever we have any dead time in the system, whenever there is measurement delay or the overall the original process transfer function has a delay, they cannot be accurately handled. So delays or dead time cannot be accurately handled. So does that mean if we have a delay we cannot use Laplace domain analysis? So that is not entirely true. We can do sort of an approximate analysis, and that can be done by approximating this dead time term. So we will have to approximate this, and that approximation is done by what is known as a Paddy's approximation. So the Paddy's approximation can be of different orders. Very commonly we use the first order Paddy's approximation. So it says that if you have a transfer function of this form, which is a pure delay, we can approximate it as 1 minus Tm over 2s divided by 1 plus Tm over 2s. So we sort of split the contribution of this transfer function as some numerator and denominator dynamics. So if we use this for our example, so for the blender system, we get 1 plus 8.33 10 raised to minus 4 over 3s plus 1 into Kc 1 and 1 minus. So, let us say for this system we use Tm is equal to 1. Then we will have the corresponding Paddy's approximation as 0.5 s 1 plus 0.5 s. So, now if you try to simplify this system, what we will get is three s plus 1 plus 0.5 s plus 8.33 10 raised to minus 4 kc and 1 minus 0.5 s equal to 0. So, if we simplify this further, what we will get is 1.5 s square plus 3.5 s plus 1 plus 8.33 into 10 raised to minus 4 kc minus 8.33 into 10 raised to minus 4 over 2 kcs equal to 0. So, in a condensed form, what we will get is 1.5 s square plus 3.5 minus 4.165 10 raised to minus 4 kc s plus 1 plus 8.33 10 raised to minus 4 kc. So, now if we use the Ruth or Hurwitz criteria, we will have 3.5 minus 4.165 10 raised to minus 4 kc should be greater than 0, that is kc should be less than 8403. So, you can note that earlier when there was no delay in terms of measurement, I could use infinitely large controller gain and the system would still remain stable. However, the moment I have a measurement delay of let us say 1 unit, automatically the controller gain reduces to 8403, and you can easily test that if the delay in the measurement keeps on increasing, the stability limit will also keep on reducing. So, if there is large measurement delay, then the maximum controller gain which you can use without affecting the stability or without destabilizing the system keeps on reducing. So, by using this Paddy's approximation, we can approximately do this stability analysis, and the reason why I say approximately is, let us say for this particular system, if I use Kc equal to 8000, then by Laplace domain analysis, so if Kc is equal to 8000, Laplace domain analysis tells me that closed loop system will be stable. However, if I actually implement or simulate this particular system when Kc is equal to 8000, what I will realize is, or in reality, Kc is equal to 8000 is unstable. So, why is this happening? My Laplace domain analysis is telling me that the maximum controller gain I can use is 8400. However, even if I use Kc equal to 8000, for this system the oscillations are growing and I get instability. The reason for that is the way we are doing this stability analysis is that we are approximating the delay as by Paddy's approximation as a proper transfer function of numerator and denominator, which is not true because that is an approximation. So, whenever we do approximation, we are going to get an approximate stability and a limit which is not going to be true, and you can see that it is quite a drastic difference, that even if I use K3 equal to 8000, which is quite low compared to the stability limit, I am having unstable system. So, especially for that reason, we need to have a method which would not require such an approximation of dead time, and that will be possible if we do the stability analysis in frequency domain. So, we will take a break here, and when we come back we will see how these systems with dead time the stability analysis for systems with dead time can be accurately handled if we do the analysis in frequency domain, which is inverse time domain, as against a Laplace domain, which is a complex time domain. So, we will stop here for this lecture, and when we come back we will look at the frequency domain stability analysis. Thank you.